Good afternoon, everyone. Can you guys hear me? Yeah? Okay, so that's good. So I will spare you my last name. You can call me Avijit, okay? So I'm beginning to forget my last name too. So, but this work that I'm going to talk to you about is a culmination of multiple years of work with multiple people whom I don't want to disregard at all, so I put them right up front. And even this list is probably short, and because you will see the the breadth of the work is much more than what we can imagine. With those people, there are others who are in the periphery who contributed to this work. So there are two things, and if I have a pointer somewhere, let's see, does this work? No. Oh, which is in this nice album, yeah. So, you know, I have to do my both hands. There is a biblical character in India called Sabyasachi, who used to have both hands working like he's either left-handed or right-handed, doesn't matter. I don't know if there are any others, but if you know of that, so I have to become Sabyasachi now. I'm going to just go with this for now. Okay, so we're going to talk about two things. One is the Gulf Stream, and then the warm core rings. And I think everyone knows that the Gulf Stream, as it moves from Hatteras all the way downstream, it forms these unstable meanders and creates a lot of warm core and cold core rings, right? Everyone who are graduate students have learned that from Charlie and others, right? Okay, so we are going to talk about those two, and spatially in this time period, and because 1993 is kind of the starting of a full year of satellite altimetry data. So TOPIC started in October of 1992, so the first full year of data that we have from TOPIC's Poseidon is 1993, and so we are going to show some of those results from altimetry. Okay, so now I can use this guy. So the outline is basically three things. First, can everybody in the back see this? Okay. So the meandering of the stream, and remember these longitudes 65 to 60 west, and I'm going to show you that the Gulf Stream behaves differently after and before these particular region. Then we are going to talk about some of the secular changes that we have observed, and this is where the 1993 comes. And then I'm going to talk about some of the recent work that my master student did on creating a census on the warm core rings. Okay, so any talk on Gulf Stream should probably start with this chart, and everybody knows this chart, right? Okay, the Franklin Folger's chart. I was trying to find out if the exact year, and I found that there is no exact year but a guesstimate of 69 to 1778, and we became independent in 1776. So it's it spans a large number of years there when Franklin, and everyone knows how he came up with this chart, right? Okay, so if not, then we will talk about basically sugar and tobacco is responsible for creating that particular chart. Okay, so anybody who is interested to know more, we can discuss that. But that was what, 200 plus years ago, and when we run today's numerical models with the supercomputers in power, we probably do a pretty good job of recreating that path. Then we understood for some years that the Gulf Stream actually has these, it's a system, and there are these recirculation gyres in the Sargasso called the southern recirculation gyre. There are these called the slope gyre. There is a barotropic, baroclinic part of those. And then eventually the Gulf Stream goes all the way into the European seas, carrying a lot of heat. And in fact, that's how it heats up the atmosphere above it, and then it affects the weather in Europe. And as well as all the, and this is also, now we know that this is the part of the western limb of the surface limb of the Atlantic meridional overturning circulation. That's a long one for a short name, AMOC. That's much better, AMOC, right? And we understand that, and there have been lots of studies to relate the Gulf Stream and how it responds to the overlying wind fields, which is the NAO, or how it impacts by the Labrador Current, which pushes the Gulf Stream or not. So one thing that is missing here are the eddies of the Gulf Stream, right? So that's the large scale pattern of the system. But there are these mesoscale rings, the warm core rings, the cold core rings that are formed, and now we know from satellites that this is the real picture of the Gulf Stream is in a synoptic framework. So naturally, that's not the end of it. There is also, if you think about just the Gulf Stream, how do you actually characterize it? So one way that people have started characterizing is by its northernmost gradient of temperature, or what is called the Gulf Stream north wall, right? And that will give you the position of the stream, and that will give you some marker of its movement over the years. So and then there are these, this blue line is the deep western boundary current, and this is probably oleander. So or maybe that one, right? That looks more like the oleander. This is probably another lines that someone did. So the idea is that the Gulf Stream, as it separates from Hatteras, it does move into this region where the New England Seamount is, and forms these large amplitude meanders, which leads to these warm core rings, which has its impact on the ecosystem in Gulf of Maine, Georges Bank, Mid-Atlantic Bight, and the shelf region over here too. So from North Atlantic Oscillation to the little biota on the shelf has an important link with this thing that we call the Gulf Stream, right? So naturally people want to observe it. In today's world where the climate is so important, climate change is so important, people wants to know how the stream behaved over so many years, right? So that's the point that we're trying to get here and see where we stand today. So as we mapped the Gulf Stream in 2017, and thanks to Benjamin Franklin who started mapping it, so now we can map not only the mean circulation but also the synoptic Gulf Stream and its eddies, and put numbers here of the temperature that we see and all that. And this kind of charts have been produced after the invention of satellites, and when the satellites were collecting sea surface temperature pictures, and we have them now from 1977 till now, and it's still ongoing. So this is a typical map that we can have twice or thrice a week that is available to us. So let's look at some of the work that has been done in identifying the Gulf Stream north wall position, and the way people have done it. And here are two lines here. This is 1950 all the way to 2010 here, and I don't know if you guys can see it from the back, but the two lines here, one is called the Taylor-Stephen index, the other is the Joyce index, and the Joyce index is the one with asterisks or this dark blue line, and this one is the dashed line is the Taylor-Stephen index. Both are for the Gulf Stream and they're all annual, but if you look at them, they match at times, they don't match at times, right? So there is a difference between the two. Now if I take a spectrum of these two time series, then this is what I get. The green is for the one from the Joyce index, and the dashed is for the dashed line from the Taylor-Stephen index, and you see that both of them has a near decadal peak at about 7 to 10 years, and then the Joyce index has a 5-year and a 3-year peak, whereas the Taylor-Stephen index does not have such a peak, right? So the content in this Gulf Stream index, or the two Gulf Stream indices, are different. And so when I started looking at this about maybe 6-7 years ago, when trying to use this for a North Atlantic oscillation study, I ran into this, and then I said, what's going on here is something that we need to really understand. Both are Gulf Stream index, but one gives a 10, 5, 3-year peak, the other gives a 7, 8-year peak. So if you go back and look at how these indices were constructed, what you see is that the Taylor index goes from, or is computed with the some EOFs of the north 12 positions that are given between 79 degrees west and 65 degrees west. So it's this portion of the Gulf Stream is the raw data that goes into that index calculation. Whereas the Joyce index, which is more of a subthermocline, or not subthermocline, subsurface measure, it's the 200 meter 15 degree isotherm, and he has this information from certain lines. Then he uses that from 75 all the way to 55 degree west. So Joyce index has more data, Taylor-Stephen index has a subset of that data, if you will. That's the basic difference between the two. So now if that is so, then that means Joyce index should have more information, and which it does. It has the 3 peaks, whereas the more western index of Taylor-Stephens has the near decadal peak in in the spectral analysis. Now once we realized that, then we said we need to test this independently whether that is what is happening. So this is giving you an idea that the Gulf Stream is behaving differently on this side, or at least from time scale perspective, than on this side. Okay, this is from 75 to 55, it's about 2,000 kilometers of space, right? And it cannot be just one string that does this and that. It's doing multiple things within that span of space. So what we did is we looked at the altimeter derived Gulf Stream path. So this is from 1993 to 2013. This is a separate data set from all the Joyce index and Taylor-Stephen index data. So this is the independent, and if you look at the time series, this is 70 west, the latitude of the Gulf Stream. This is 65, this is 60 and 55. You can see the similarity in 70 and 65, and you can see the similarity between 60 and 55, and you can see the differences in them, right? See, it's kind of obvious that there is this difference in the behavior in the time series itself. And if you do the spectral analysis of them, what you see is that the spectra at 70 matches with the spectra at 65, and the spectra at 60 matches with the spectra at 55, and the 60-55 spectra misses the decadal scale which is available in the 70 and 65 ones, whereas this peak here at 3 years is available, but there is no 5-year peak for 70. There is a 5-year peak for 65. So if you put all of them together, and this is what we did, what you realize is that the stream is behaving more on a decadal scale to the west of 65 and more on a 5-year scale to the east of 60. And 65 to 60, that 500 kilometer space, is more like a transition between the two spatial signatures. And that's where we tried to see if these signals can come from, or such time periodicity can come from NAO, and we saw some hints of the decadal period. We saw some hints from the 5-year period and the 3-year period in the NAO signals. This is 1966 through 2006 time series spectral signature. This is the 1993 to 2013, and you can see those peaks right there. This is the large scale impact on the stream, but the stream is behaving differently in response to such things. And remember, NAO has, and maybe Sultan can explain this much better than I can, but it has the Azores component as well as the Icelandic component, and they may be affecting the Gulf Stream in a different way. And so if we put that together, and this is what we did in this paper, what we said is that so if you think about the Gulf Stream not as one entity from 75 where it separates to 50, as this part, the separation and then onwards, is more driven by the wind-driven subtropical gyre with the baroclinic cross waves coming in and feeding into, you have a more of a decadal response in the stream. But when you think about the Gulf Stream, which is 60 west and east of that, then the Labrador current is probably pushing it and having an impact on it, which is also part of the NAO signal. So this is part of the NAO, that's part of the NAO. So when you look at the Gulf Stream as a whole, you will probably see both of those in a simple way. But if you think about the Labrador current, it's probably affecting the eastern region more than the west. If you think about the Azores High, it's affecting the western region more than the east. And that's where we left this paper at. So that's the time scale part of the Gulf Stream. So if you think about the Gulf Stream, you think that there are two regions and then there is a mixed region. So the first set of conclusions is that interannual variability of the stream is different, and it is different to the west and east, and I just showed you how. And then there is a mixed time scale response, maybe, or maybe a dominance of either of the two, depending upon how things are being forced and set up. So next is we wanted to look at, since we have the data and we realized that the Gulf Stream was behaving differently to the east and west, we said, okay, we are going to take a look at the secular pattern of the stream and if there is any climate kind of signal in the movement of the Gulf Stream. And what we did is we looked at the Gulf Stream again in at these locations 70, 65, 60, 55, and then we looked at the Labrador current as it flows from satellite altimeter data and the transport of the current as it comes through, and these are altimeter tracks at particular 5 different locations, and their mean fields were looked at against the position of the Gulf Stream. Feel free to ask me questions, and that might be helpful also. Okay, so if we look at the secular trend or the long-term behavior of the Gulf Stream, this is at 55, 60, 65, and 70. What you see is a distinct southward movement of the Gulf Stream path at 55. There is also, this one is significant, this one is borderline, and this one is insignificant. So what is happening is the secular trend in the Gulf Stream is more pronounced to the east than on the west. And there have been papers by Tal Azer and Tom Rossby and debating what is happening based on Oleander data near the western side, and one finds a trend, one does not find a trend, and that was the kind of thing. And what we found is that, well, both of them are kind of right. If you look at their analysis segments, then that matches with this idea of you see the trend and you don't see the trend. Okay, and it all depends upon where you are looking at, and if you call both of them the Gulf Stream, which it is, but you have to be mindful where exactly you are looking at. At the same time, that was the Gulf Stream path. This is the Labrador current transports, and what you see here is that there is essentially no trends in these, but as you near the Gulf Stream, there is this increasing trend of the transport. There is none here, and these are way in the Arctic region. So this increasing trend of the Labrador current is related to the decreasing or southward trend of the Gulf Stream in the east. So what we said is that this must be the idea of Tom Rossby about the intergyre exchange. So the subpolar gyre and the subtropical gyre, they are meeting the Gulf Stream on the eastern side, and that's where the exchange is happening. And so the Labrador current, as it increases its transport, is pushing the Gulf Stream farther south. And we looked at the residuals, and we looked at the spectral signature of these, which interestingly matched with what we found earlier between the Labrador current and the Gulf Stream in the east. So all that was resulted in Deep Sea Research selecting this as their cover image, and that was another story. So but eventually what happens is that the Labrador current transport increasing from 1993 through 2013, and the Gulf Stream path near here is decreasing or going southwards more because of this push into the shelf water push into the slope sea. And however, as you come near Hatteras, there is no trend that was seen in our analysis from altimeter data. So Tom Rossby, when he said that we did not see any trend, that was absolutely right. But as you move to the east, you do see that trend. Okay, so in conclusion, for the second part, 1993, this is the secular trend, and it's related to the Labrador current transport. And we also saw, which I did not show because I think I want to spend more time on the third part, but there are, in the paper we describe the link between the NAO and the Labrador Current at these 5 to 7 year scales. Remember that the 10-year scale is more to the west, the 5 to 7 is more to the east, and that was there in both Labrador Current and the Gulf Streams. Okay, so that was the idea here. So now I want to talk about the warm core rings and the most recent census. This work was done by Mahmoud Monim, a student that came to me, and we had this beautiful charts of the Gulf Stream rings, and that's when he got very interested in tracking them. I know many people, senior physical oceanographers, they would tell me that I started my life with tracking warm core rings, which is true because they have so much of importance in terms of their carriage of nutrients, larvae of different species into the slope, and then banging on the shelf break here, and which creates these streamers that comes out of the shelf, or these larvae is getting into the shelf because of these anticyclonic movements of the warm core rings, and there are huge implications of these rings to the nutrients, to planktons, and then species of these Gulf of Maine, Georges Bank, Mid-Atlantic Bight region, and this is real. A good census of the warm core ring did not exist, or so far. When we started this work in 2014, we did not have it. So we took that and worked through, and these are the questions that we wanted to address. So first thing is, what's the nature of the seasonality? Then what's the nature of the interannual variability? And the other thing is, if you have a census, then you can talk about their lifetime, you can talk about their sizes, and you can talk about other things that you will see, and whether the interannual variability relate to the NAO or the Gulf Stream Index in some sense, so that we can tie them back to the other work that we are doing. So how do you create the census? Okay, so these charts like these with the warm core rings, the WE is the eddy, and you can see them here. They're available about 2 to 3 times a week. So we have about 2,600 charts for 17 years, 2000 to 2017, right? And Monim would do like 6 months or 5-6 months in a 4-year span after lunch, tables like this laid out, and then count the rings the old-fashioned way, because these charts are not available in a particular format that could be, that's the next step, that could be digitized and then went through them in a meaningful way. But and then also you need to find out when the ring is being born and when the ring diffuses, so that's the demise of the ring. But before telling you that, so the process of the chart of creating the census is, you go through this chart, follow a set of rules about what is the birth of a ring, what is the death of a ring, and then how long does it continue. If you see a ring and then sometimes you don't see a ring within a week or after a week, then you don't count that as a ring. you have to kind of go through that kind of a logic, and then you tabulate all these parameters. Then each year of census takes about 2 to 3 days. So over a period of, I think, 6 months. We created the census. We went back through the census because some of the rings that are born in November of this month, of this year, we'll probably see them again through January, February. So if you start your census in the January of a year, the first few rings are most likely from the old times, and you have to regroup them to make sure that you are not counting rings twice and all that kind of thing. So all that neat little things have to be taken care of, which we were good at. And so this is an example of the census for, say, 2005. So this is the date of birth of the ring of 3rd of January 2005. This is 6th of, so see, this here is a great example. So this guy was actually seen on that day, or the first chart of the 2005, but it was actually born in 2004. This was born in November of 2004, right? So, and then you can have their latitude, longitude, where they were born, the size at birth, and then date of absorption or date of death, and then where you saw it last. So that will give you, and the time, and that will give you a lifespan of the ring, right? And at the same time, the last seen sizes are generally like this. Some of them are big because they get attached to the Gulf Stream. That's also a demise or absorption. So created these kinds of census, and then what you can do is ring birth. You can create the seasonality of ring birth. So summertime is the most active ring birth period, June, July, August, right? And this is the seasonality, and this is typical that we knew from earlier census that was done back in the 80s and then one in the 90s, but based on 5 years of data. So they were and this information was known looking at rings year by year, but this is based on 17 years of data. Now why does it happen like that? So there is this idea that seasonal cycle of eddy kinetic energy is high in the June, July, August period, so that also shows that the rings are more during summer, so you get more EKE. This is from altimeter data with Jai et al. Paper. Similar thing was done by a model, I think this was ROMS, run for 50 years or something like that, Kang et al. 2016, and you can see the EKE from the model run. So they assimilated all data into this model, and then this is the red box where the worm core rings are, and you can see the EKE picking up again in the summertime at most of the upper thermocline depths. Okay, and that matches with this idea of seeing more rings in the summertime. So match is good, and now we have a feel of how the rings behave. So what we did is we wanted to look at the longitudinal distribution. So we divided the whole region in 5-degree bins. So 75 to 70, 70 65, 65 60, and 60 55. And right here in the middle is the New England seamount chain, and you can see the drastic difference between ring formations to the west of the New England seamount chain and to the east of New England seamount chain. One thing that was interesting is that almost equal number of rings were formed in the two bins, 65 to 60 and 60 to 55, and we don't know the reasons for that, but that's what it is from 538 rings. So if we look at the age distribution, you can see that we divided the age, meaning the lifespan from date of birth to date of absorption. If that is less than a month, that's the dark blue. Then we had 4 groups, then 30 to 90, so month to 3 months, 3 to 6 months, and then 6 months or above. And you can see that there are few rings which lived more than 6 months, and there are some rings which, there are no rings which live more than 6 months here in the 75 to 70 west bin where the rings are formed. And the other thing to notice is that as you go east, your lifespan of the rings increases. Now you can say that, well, that's just because they are farther out from the shelf break. Maybe so, and that may be just a simple reason. The size of rings. So this is the rings at birth, and the sizes are again in 4 different bins: 50 kilometers or less, 50 to 100, 100 to 150, and 150 plus. These are the radius of the rings. And what you see again here is that as you go east, you have bigger rings. Okay, so the number, the age, and the size increases as you go from 70 to 50 west. Okay. With that information for 17 years, we could do a probability analysis, which was done by Monim. So essentially for lifespan or size, so given that a ring is formed, what would be its size and what would be its age? So how long will it live and how big it will be? If I see a Gulf Stream meander about to form an warm core ring, would I be able to predict that? That was the idea. And with some probability, we have now the statistics to do that from 17 years of data. And that's what we did. We created these lifespan probability indices, and you can see that. And so greater than 90 days, there would be no rings born in January, February, March in this region which will have anything to do with any ring that is of any age. Okay. Similarly here, now these are based on 17 years of data, so the voids that you see are based on having less degrees of freedom. So if we do not have even 6 observations, we do not count that in the probability, but when we have more observations, we count them in. But the interesting thing is, say for a month of June or July, if so for June, say 65 to 60 west, if a ring is formed, it has almost 1/3 of a probability of being in a month, 3 months, or more than 3 months age. As you track that ring, if it passes, then the probability increases of it being more or longer lived. So these are the things that we could begin to use, I think, for tracking the rings and probably even getting to predict how it will impact the shelf and slope ecosystem. Same thing with size. We could see when a ring is being born, how much size it will be and what's the probability of its being a larger ring or a smaller ring. And you could play this game if you have enough degrees of freedom. And one thing that we are trying to do now is to go back to 1980s, because this is based on 17 years of data, 2000 to 2016. We want to go back to 1980s and increase the the region-wise analysis to come up with better degrees of freedom on these. Okay, so one other thing that we noticed, which is very interesting, I think, is that the number of rings, the average number of rings over this 17 year period is about 22, which is much larger than the previous set that another student of mine did back in 2004. And we checked this with both data sets, but the average was like 15, and now it is like in the 20s. And so if we mix the two, and we are yet to, so this is the previous analysis, and this is the present analysis. And you can see that the average number in the 80s and 90s have increased to about, especially in the early 2000s, there were more number of rings. And we went back and checked all of these against these, and it is indeed there are a lot more rings in the system in the 2000s than now, and it is coming back to this kind of numbers now, but which are still more than the average of earlier period. Yeah.
Could this be due also to the fact that in 80 to 2000 you're using SST and the other one is using CSAPS, right?
All of them are using SST. All of them are using SST. Yeah. 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 This is actually AVHRR. Is the same as far as that is concerned. It is, and in fact we checked against the BIO, so there could be an analyst problem, and we check against the BIO data for 2000 to 2004, and they are showing even more rings than what we are seeing.
Have you looked at like satellite launch, new technology launch, that jet detection could improve?
So these are from satellite data.
Yeah, but satellites change.
VHR is staying the same.
These are from satellite as well as in situ. It's a mix of multiple data sets. And the AVHRR question is very interesting because from AVHRR data, which is 25 kilometers, the mesoscale resolving resolution is at least 75 kilometers. And so we don't see the rings from altimeter in any case, and they're so close to the coast. And the resolution, even if it is, I think with AVHRR and the new satellites, their infrared signatures are much less than the eddies have radius of what, 50 kilometers. So even if we have like 6 kilometer, I don't think even the early AVHRRs were what, 1 to 2 kilometers of resolution. So I think we are good there. But we are going to revisit this, and the other thing that in connection with this is that the shelf and the slope has become really warmer in the past 2 decades, and that is a well-known fact. And Glenn Gawarkovich, who is in the team, is looking at this, and recently he presented this thing in some other place, and in the recent MapBomb meeting this was presented also. And it seems like a consensus that things have changed in the slope. Things are changing in the shelf, and we have to come to a understanding of what is driving that change. We don't know that yet, but so I think this is a real open question: what caused this? The other thing that I wanted to mention is that when we did the first study, the Chaudhary et al. 2009 paper, there was a distinct relationship between the warm core rings and the NaO. When we looked at the warm core rings and the NaO for this period of 17 years of study, we could not find a relationship, and that was the first time that I realized that something has really changed, and the NaO is not matching with the warm core ring the way at least it has matched before. However, it did match with the Gulf Stream index, with the Taylor index, and this is the rings from 75 to 65, and the index is Taylor index because that goes only up to 65, and you can see a distinct as the Gulf Stream moves north, you have less number of rings. As the Gulf Stream moves to the south, you have more number of rings in that region, and that matches with that idea. P-value is pretty good. Okay, so that's the census part, and then offshoot of that is something that we are trying to do is if we have the number of rings, and this is some work by I think your group here, Charlie, and so this is a very interesting paper that you guys have looking at warm core rings from the Oleander data itself. So I thought, and before I knew that Sultan will invite me here, I was looking at Oleander data, and I did look at some of the data because what is causing those number of rings in the Gulf Stream could be that the baroclinic instability is forcing it, okay, and that means that the shear at Hatteras might be responsible for it in some sense. And if I think about the shear of the Hatteras and shear of the Gulf Stream at Hatteras, then to go back and find out how the Gulf Stream was like, I thought Oleander would be a good data set to look at. And so I did look at that data, and this is an example of what Charlie and Tom and others have done. And so this is the Gulf Stream, and the idea is that the shear here, which is around 73 west, might be related to the warm core rings that are being formed off the stream. And so I did a simple thing that one could do, is that the transport of the Gulf Stream from Oleander, that block that you saw, is in say the January or the winter time transport, and this is on the y-axis is the warm core ring births in the summertime, June, July, August. And there is a significant correlation that we find, and we are still trying to figure out, is this real, is this a fluke, or there is real, and Charlie and I were talking, and Tom is also thinking how best to, because I understand that these are interpolated to January, and there is much more data in the Oleander site than just these mean values for a particular time period. So we might want to take a look at this kind of a relationship in much more detail, in a more dynamical sense. So
why January?
Because I thought there is a very good question. Actually, this baroclinic instability waves that are triggered in, say, winter would take some time to propagate through the stream, and that lag has been shown by that Kang et al. Paper and the to be about 3 months. So that's what the idea came, that maybe there is a way that if I could track the January, then I could see the summertime. So I took it from 3 to 6 months. But what happened is that I have the things on my laptop, and not only January, if I take February interpolated, March interpolated, April interpolated, is the same result. It changes from 0.62 to 0.625, 0.63, things like that. So there is something there. And the other thing that I was mentioning to Charlie earlier, that the Oleander dataset also gives you the slope transport, and if you add the slope transport to the Gulf Stream and add it to the mix of this baroclinic instability or the shear, the number, the R was I think 0.62 here, it becomes 0.69. So that's even higher, but I mean, all these needs to be sorted out. So putting it all together, I think what we have seen, and that is why I say in a few new things, there are these two different time scales. So I'd like to encourage the young upcoming physical oceanographers and anyone interested in the Gulf Stream to think about Gulf Stream not at one point or an average sense, but think about the Gulf Stream as a continuum that can change in its behavior as a response to the large scale atmospheric or other ways like the Labrador Current and so forth. So the time scales are really different between east and west. So that's the first takeaway from this talk. The second thing is that the eastern part is more linked with the Labrador Current, and that is shown in this secular trend, and the Gulf Stream is actually moving further to the south as you walk to the east. Okay? And then the last thing is that things are changing in the slope C. Number of rings have increased, and it has lost its correlation with the NAO, which was there and now it is not there. And the other thing is that why are they more? And even the larger question is probably, is the Gulf Stream, knowing the Gulf Stream at Hatteras, like the Oleander, will it lead to a predictability of the warm core rings in summertime? That will in fact be a very incredible thing for the fisheries folks to know and to track the ecosystem in that sense. So with that, I think like to acknowledge multiple funding sources, and then Jennifer Clark, Roger Pettipus, Terry Joyce, Frank Smith for their help. They really helped us a lot in multiple ways. And thank you, and I have to say happy Diwali to everyone today.
Time for a few questions. Yeah, you mentioned that at the end of the second part that there's some connection between this and the NAO, but you didn't have time to go into that. So can you say a few words about sort of how the NAO sort of tied to the change in the Labrador transport and the Gulf Stream?
Yeah, sure. So one way that you can think about NAO is that you have this Azores high and the Icelandic low. The Icelandic low comes all the way into the Labrador Sea, right? And that forces the Labrador Current and the convection that happens before the Labrador Current transport increases. Now, what we have seen in right, and in recent times, Labrador Current in that particular region, let me go back and Yeah, so so the Labrador current here is, its transport is increasing, which I think is due to a multiple effects of the shelf water that comes in from the NAO driving. Okay, and in the paper, Jim did a calculation of the shelf water volume that is being carried in the shelf, which is pushing this Gulf Stream. So you can see that the transport not only increases, but the increased transport has an effect on the shelf water volume. So that's the hypothesis linking the transport there to a larger shelf water volume, which is actually pushing the Gulf Stream.
Yeah, I was just a little bit surprised by that, because if you just naively look at the annual index, the index itself is actually weakening during the past 20 years or something like that. So it increased from the 70s to 90s, but then the annual index actually increased. But that's a very simplistic index. Obviously, it doesn't describe how all the winds and stuff change. So if you just naively take the annual index as the driving force, then one wouldn't expect the increase in the volume of water.
That's actually interesting.
There's typically the thought is that when the NAO is weak, then the Labrador current sweeps around the Grand Banks more easily. And when it's strong and there is deep water formation, the Labrador waters tend to go off to the east.
Yeah, so that's just opposite to what I naively think.
Yeah.
Yeah. Okay.
So with this, so there's opposing trends in the Labrador current transport and the Gulf Stream latitude. Is there a lag relationship between them? Can you tell which one is leading the other?
Yeah, I think I really have to give you the DSR paper. We discussed a lag there, about a year.
Okay.
And not only a year lag here, but there is this lag between the transport here of the Labrador current and the movement of the Gulf Stream here.
So
It's very interesting, and so that might be completely a different mechanism of how the convection happens and how the deep western boundary current happens, which is not at the surface. What you're looking here is at the surface, but there is something going on underneath that is even more. Remember this cartoon that I had? That's probably the best that I have now, and I can show you that. This one. So this guy is actually a subsurface flow that originates due to convection in the Labrador Sea and multiple other limbs that comes in. Yes.
Okay. It's interesting to see the form called rain. Are those rains all at the cyclonic?
Sorry, are those rings?
All the rains at the cyclonic?
Yes, yes, yes.
I
The-
understand if the rains are north of the Gulf Stream. How can I understand?
Oh yeah. Do you have a? Yeah. That's actually so. This is not very good. So the Gulf Stream comes here, right? Okay. So this is your Florida current, and then it separates out. So what happens is, as you go out, this thing starts meandering, right? So few days later, this particular high amplitude thing will become like that, right?
Where does the easterly come from?
So
you're gonna have the eastern is coming off.
No, it's the baroclinic instability will pinch it off.
Oh, they are the same as the Gulf Stream. Where can we get
This water is Gulf Stream water. That water is Gulf Stream water. I mean, this water is Gulf Stream. But what it is trapping, why it is a warm core, the trap here is the Sargasso water. Right? So that's why it becomes a warm core ring, as opposed to when you have a trough here, then it is trapping the slope water. Right? So then this becomes more like a cold core ring, because this water is colder than the Gulf Stream water. Both warm core and cold core will have the Gulf Stream on the side, but one will move anticlockwise, the other will move cyclonic, right? Anticyclonic and cyclonic, and it will trap warm or cold relative to the Gulf Stream. Does that?
Yeah, it really look like the blocking the atmosphere, but we can disable that.
So the last question will be from Dr. Thomas.
So I want to go back to the question Edmund asked about the relationship between NAO and the Labrador current.
Mm-hmm.
I was thinking maybe an alternative explanation of this would be the amount of fresh water from the Arctic as it increases. So that would amplify the Labrador current and help push this, which would have maybe some relationship, but very little relationship to the NAO.
No, you're talking about the Arctic melt.
Yes.
There are papers hypothesizing exactly that. I think multiple processes are in the play, and one of them is very well be just that. And I can point you to, there is a group called Yashiev in BIO, Igor Yashiev. Yeah, and he has done excellent work on exactly that kind of ideas. There are multiple papers on that, trying to link the Arctic melt to the Labrador and effectively to the Gulf Stream. Yeah. I mean, these things are multiple processes are acting, and effectively what we are seeing in the Gulf Stream is its response to multiple factors. So you have to choose out what you want to look at, and one of them is absolutely right, that process.
So just a reminder that we will go to lunch from here, and then at 1:45, Dr. Avijit will be there and available for graduate students to speak on it. So let us thank him for such a wonderful presentation.
Thank you.